divided by m.
Yes.
The charge times the magnetic field times the mass. Omega, if angular acceleration is 0, is just change in angle over time. It travels through what angle in how much time? And so, since we're trying to find time, the time it takes to do it, and we know theta, we just set these two equal to each other and solve for t.
You solve for the change in t as opposed to t.
Well,
It's the same.
technically, yes, it is the change in time. It is the time it takes for it from the moment it enters to when it hits that point. But the reason, it's the one place where I play fast and loose. One of the points that I'm just going to assume that the time is equal to 0 when it enters the room. So the time would be the change in time.
So you're saying 1.31 divided by whatever the time is equal to QB over N?
Yes.
Okay. Okay, that makes sense.
Aren't these fun problems? The next one's even more fun.
Oh.
I'll read it to you and then we'll take a small break before we come back to it. On a planet where the acceleration of gravity equals g, two metal rails of length L are leaned against the wall as a ramp at an angle theta to the bottom. So basically, two rails. Angle theta.
Physical demonstration.
Yeah, if we had oh, we can do it.
Another meter sig?
There is nothing but the best for you guys.
Thanks. Okay.
All right, angle theta with the bottom. There is, of course, a wire connecting the two of them down there, and I've got a metal bar across here which is going to slide.
Oh, I remember.
The two bars, the two rails, those are the rails, are a space and distance d apart. The bottom of the rails is connected by a superconducting wire. And a resistor of resistance R is spliced into this wire. So the only resistance you have to worry about is the resistor that we've stuck into it. Metal bar is placed on the rails perpendicular to them and parallel to the wall. So like that. And a distance z from the bottom. So that when it's released, it will slide down the rails. A magnetic field of strength B is turned on, so it bathes the entire setup and it's pointing upward. So I got a magnetic field going up. Question A. Only 6 parts. What is the initial area vector enclosed by the circuit? B. What's the initial magnetic flux? C. As the bar slides down, what is the direction of the current flowing through the bar? D. If the current were running through if a current I were running through the circuit, what's the total force acting on the bar? E. What is the speed of the bar as a function of time? And I believe that is a calculus problem. And then F. What is the current in the circuit when the bar has reached its final speed? Yeah, that one, I like that problem. Students were not as pleased with it, but. So anyway, why don't we take a small break, stretch legs, and then we'll come back and we will crank through this one. And you will be delighted, no doubt.
The students are not as pleased. That's since they couldn't appreciate it.
Yeah,
I wish they would.
Yeah, just hearing about it.
The heathens. All right, so we got two rails, and I just realized we can't probably we'll only saw part of it. So we basically have two rails right here leaning against the wall. There's a bar that's going to slide down. We assume that Z is long enough so that for the last problem, wherever it is, I had it in my hand. And There we go. Because the last one is what's the current when the bar has reached its final speed. We assume that z is long enough so that the bar never actually hits, so that the bar will actually hit its final speed. So part A, the area vector. How do you find area vector?
Perpendicular to the surface.
Yeah. So my area vector is going to be either that way or this way, and I'm just gonna make it that way. What's the magnitude?
The area.
Okay, and the area is, well, z times d. That's d right there.
ZD.
So the magnitude of my area vector is zd. Now the question is the angle, because so I've got theta right there, so if I sort of break this up into its components, if that's theta, this angle here is theta. That means this angle right here is the complement. Draw that a little bit bigger. So this is the complement of theta, and this angle here would be theta. So if I'm expressing in terms of I hat and j hat, which will be convenient for something we do later, it would be zd times the sine of theta I hat plus zd times the cosine of theta j hat. That's my area vector.
Why is there absolute value signs around the area vector?
Because that's the representation of the magnitude of the area vector, and the magnitude is zd.
Okay, yeah, that makes sense.
But the question was for the area vector itself, and so that's what this is.
No values or anything. So that's the answer to A?
That's the answer to A. See how simple this problem is?
I don't know. We already pulled up the complementary.
Yeah, would you mind going over the components one more time?
All right, so I've got, that's my surface, and my area vector is in this direction.
Yeah.
Yes.
So my area vector is that way. I give you that this angle here is theta.
So that.
Well, I'm gonna break A up into its components. I know that the hypotenuse is the magnitude of ZD. So that's theta or that's theta, one of them is.
And the bottom one?
Well, that one? No, actually, it would be that one. If this is theta here, this angle here is theta. Those are the same angle.
Oh.
This is a right angle here, so this is the complement. That's a right angle, so that has to be theta. So my horizontal component is opposite theta, so that's why it's sine. And the adjacent component is cosine.
Okay, thank you.
Okay, so we still could tell it to get
Yeah.
sine or cosine?
Yeah.
Okay.
Now, what's the magnetic flux?
Well, that one. The magnetic field across the area,
Ooh, no, not cross.
solid.
If the magnetic field is constant, then it's just B dot A. If it's not constant, then that's a calculus problem, and it becomes B dot dA. But in our case, B is constant. And it is acting straight up. I know that B, the magnetic field is just equal to B times, or B J hat. So, B dot A, well, I just found the A right there. When you're doing a dot product, you multiply the parallel part, so there is no I hat part, so that part goes away. So my magnetic flux is equal to Z D B cosine of theta, j hat, no, sorry, dot product, that goes away. ZdV cosine theta.
Why do they cancel out again? Or are they going in opposite, in the same
Why
direction?
does what cancel out? The vectors, the unit vectors?
Yeah, the J.
When you do a dot product is a scalar product, and so when you multiply the parallel components, so when you multiply that times this piece,
You just dropped it to
J
zero.
dot J is one.
Zero.
Oh, J dot J. Okay, that makes sense. Okay.
The J dot I is zero. Because dot product cares about parallel. Unlike cross product, which cares about perpendicular.
Oh, that's why we don't got a sign there up there. Okay.
Yep.
Sure. Okay.
As the bar slides down, what is the direction of the current flow through the bar? All right, so as the bar slides down, what's happening to the magnetic flux?
It's decreasing.
Okay, so it wants to create a current that's going to try to offset that. So, well, my current's either going to be going around counterclockwise or clockwise. Which one is going to cause an increase in the magnetic field in the middle?
A.
The current's going up.
The magnetic field's coming this way.
Yeah, so the current would be like this, so it's ramping up.
We want,
Oh, okay, so you're doing it around like that?
yeah,
I'm trying to figure out,
oh, sorry.
okay, yes, and chance,
Okay, so the current going across, the current's going up the resistor from the overhead field.
so the current's going that way?
Yes, because
Okay.
then the electric field will be coming out, and that's offsetting the loss of electric flux that's coming out.
Throw the word magnetic instead of electric, I guess.
Oh, magnetic
It
flux.
seems to be your thing.
I understand it's magnetic, I don't like you saying electric.
So the current would be flowing around like that, because that will produce a magnetic field coming in this direction. So going through the bar, it's coming this way or that way, it's in the k hat direction.
Wouldn't that be the negative K half direction?
No, I said I is this way, j is that way, which makes k this way. And then when I go from this view to this view, I basically take this and so my rails are like that, I take it and I rotate it like that. So k is pointing my thumb direction right there. K is still pointing down.
Or aren't we saying that the current is going
Through
up
the
the
bar.
resistor? Oh, it's through the bar?
Yeah.
Okay, never mind. Okay, I was thinking for the resistor.
Okay, the question specifies through the bar. Because otherwise, if I didn't do that, then somebody might say k hat, somebody might say negative k hat, and then you're going, well, I guess eventually.
That makes sense.
All right, as the bar slides down, what's the, oh, we did that one. All right, so if a current I were running through the circuit, what is the total force acting on the bar? Well, what is the formula for a force on a current?
What is the third force for the bar on the current?
What is the force on a current in a magnetic field?
Current times length of the circuit, I guess, crossed with the magnetic field.
Not DL.
No, we're not doing a differential here.
Oh.
The DL shows up with Bios of R
Oh.
when you're writing the magnetic field. All right, so current IL, well, that's just the length of the bar that the current's flowing through, so that's, the length is D. My magnetic field is B, but we do need to sort of worry about this. This is D in the K hat direction. And B is in the J hat direction. So that's B, J hat.
Oh.
So what is the direction? So I have IDV.
JK. Positive. Negative. And they're both positive, so we go this way. So K, J, and then, so it's I? Negative I?
It's negative I.
Oh, it works.
even better, it matches what I've written down here.
For the length component, I guess, you're just taking the length of the bar, of the current that runs through the bar, is that what you're taking?
Yes, because the bar might be longer. I mean, so if my rails are this far apart, but my bar is this long, the current's only flowing through this part of the bar. So that's the part that is L. Other questions up to here?
What do you mean by the force on the bar?
As I have a current, with the current flowing through the bar, there will be a force acting on it. Because any moving charge through a magnetic field, there's a force involved. Any moving charge that's not in the direction of the magnetic field, there's a force on the bar. Magnetic field is this way, the charges are flowing that way, and so therefore there's a force on the bar.
Did we also state if the bar had mass or not?
Let's assume the bar does have mass.
So isn't there also force due to gravity that rolling down?
The question in, yeah, the wording that I gave was the total force, but that is actually just the magnetic force. So you are correct. We do need to add in other forces.
Is there any friction?
No. Yeah, let's not complicate it that much. All right, so what we have there on the bar, we have a normal force acting this way. We have weight acting down.
Right.
And then we have a magnetic force that we figured out is acting in the negative I hat direction. And that's the magnetic force.
Just a side note, would this come under other? If we're doing,
So
F-tone?
at this point, we would have thrown in
That,
an extra M in there.
okay, cool.
From down. From Tom.
Well,
All right, the direction of acceleration is this way. So we need to break some stuff up. The only thing we're not breaking up is the normal force.
No?
Yes, the normal force.
The Y.
It's perpendicular to the acceleration.
Okay.
The other two are not. All right, so if we break the forces up, again, breaking weight up, we did it plenty of times in 251. Down the rim, since I gave you the angle with respect to the horizontal,
Would be what?
just mg sine theta,
Sine.
mg cosine theta.
Right.
Normal force this way. Breaking the magnetic field up, breaking the magnetic field up is perpendicular to the weight,
Mhm.
and so,
What
well, I
if
know it's that way and that way, and so this will be FB sine theta, FB cosine theta. Because they're perpendicular, the parallel, anti-parallel parts are the opposite trig function. If that's cosine, that's sine.
Okay.
that makes sense.
And so now, we're trying to find the total force. Oh, so the total force, I guess it depends on how we want to express it. Oh, well, I know that those forces cancel out.
Mhm.
So the total force would be mg sine theta minus fb cosine theta. And at this point, I'm gonna change my coordinate system. I'm gonna call this, I'll call it I2 hat. This is my I2 hat direction.
Could you, I know they cancel out, but I can't figure out why right now. Could you
Why
elaborate?
those cancel out?
Yeah.
The direction of acceleration is down the ramp,
Yeah.
which means that perpendicular to it, there's no acceleration.
Oh, there can't be.
Yeah,
So
if there was acceleration perpendicular to the ramp, that means the bar comes off the ramp or digs into the ramp.
Does they have to be zero? Like
So,
they have,
those would have to balance out.
somehow, yeah.
So,
Okay.
We assume that the rails are strong enough to withstand whatever that is.
Okay.
Although it's not explicitly stated, I think if you were not making that assumption, the problem becomes at least 4 times harder.
At least. It probably gets exponentially harder.
Can we just say it's broke so we can't solve the rest of the problem?
Ramp breaks.
Ramp breaks, can't solve.
If the ramp breaks, then the current's not flowing through it, and therefore that problem is invalid. So because there is a current, the ramp's not broken.
Dude, I won't pull that one. Different class.
All right, so the speed of the bar as a function of time. Now we get into the calculus.
Yes.
There we go. That's the enthusiasm of 1.
Let's do some calculus. Some general calc.
Hey, remember, physics is what gives math purpose.
Before physics, math was just a lonely soul.
Well, math gives physics stuff, right?
I wrote on the board years ago, there was Demi had the class after mine, and I'd written on the board, physics is what gives math purpose. And when I came back the next day, it was written underneath it, math is what makes physics fun.
What was your response to that?
I left it at that.
Isn't it what makes physics possible?
Yeah.
More so
All right.
how you explain it.
So what we have here is the total force mg sine theta minus FB cosine theta, and FB is IdV. Cosine theta is equal to mass times acceleration.
Uniform force.
Well, acceleration is dv dt, because I'm trying to find v.
And do our m's cancel out, by the way?
So if I divide by m, I get g sine theta minus IdV divided by m cosine theta is equal to dv dt.
Okay.
The trouble is,